Hello dear students, welcome to Pen and Paper Chemistry on YouTube. The topic that we are taking up now is Kohlrausch law and its applications. Now in the earlier video we have already discussed the graphs related to the molar conductivity, how the molar conductivity of strong and weak electrolytes varies vis-a-vis the under root of concentration. Now we also notice that in the case of strong electrolytes there is a linear relationship and we can determine the molar conductivity at infinite dilution by simply extrapolating the graph. How do we determine the molar conductivity of weak electrolytes? Let's start with that. Now if you recall this graph here, we had drawn the graph of molar conductivity of a strong and a weak electrolyte, and we also noticed that for a weak electrolyte we cannot determine the molar conductivity simply by extrapolating the graph, because if you notice it is almost going parallel to the y-axis. To explain this or to find a solution to this, Kohlrausch gave his law based on the observations that he made regarding the molar conductivity of strong electrolytes. Now the data that was used by Kohlrausch, I have tabulated it over here. So we've got the molar conductivity listed over here. We've got KCl, NaCl, potassium iodide and sodium iodide, right? We have listed them over here. Now compare the molar conductivity KCl and NaCl. If you notice, the ion over here is the same. Take the difference of the two. Take the same difference. Iodide is the same. Take the difference in the molar conductivity of potassium and sodium. Same way, when you take the same cation, so sodium chloride and sodium iodide, potassium chloride and potassium iodide, please take out your pen and notebook, my request as always, and find out the difference that you observe when you find out the difference between the molar conductivity of potassium chloride and sodium chloride and molar conductivity of potassium iodide and sodium iodide. Similarly, so one difference you find out here. Second is keep the cation as constant. So find out the difference between the molar conductivity of potassium iodide and potassium chloride, and also find out the difference in molar conductivity of sodium iodide and sodium chloride, right? Do you find any similarity? Observe, do it. You will find that you are no less than Kohlrausch yourself. Go ahead and try it. There you go. The difference between potassium iodide and potassium chloride is the same as that between sodium iodide and sodium chloride. So irrespective of the cation with which the anion is associated, its conductivity has a specific value. It is fixed value for a specific anion. Does the same thing apply for a cation as well? So let's compare. Potassium iodide, sodium iodide, difference is 23.4. Potassium chloride and sodium chloride, difference is 23.4. So irrespective of the cation that the anion is associated with, it has a certain role to play in the molar conductivity of the electrolyte. Meaning to say that although you all belong to one class, right? You get promoted as one class, but each one of you has an individual contribution to make towards the success of the class, right? and that cannot be overlooked. What I like to say, so it's a teamwork dependent on individual efforts. So each ion plays its own role in the conduction irrespective of the opposite ion with which it is associated. How do we say it mathematically? So here we've got the definition of Kohlrausch law, which is called as the law of independent migration of ions. The ions migrate or move independent of each other. It says that at infinite dilution or infinite dilution, the molar conductivity of an ion is independent. That's why the definition is law of independent migration. So is independent of the other ion with which it is associated in the electrolyte. The limiting molar conductivity of an electrolyte is the sum of the molar conductivity of its cation and anion. So if we are talking about an electrolyte like sodium chloride, so in this case the molar conductivity of sodium chloride will nothing be but the ionic conductivity of sodium, and we are using the word limiting, so we'll put a small knot over here. Here the capital lambda is for the molar conductivity of the electrolyte. The small lambda that we are using is the ionic conductance or conductivity of the cation or the anion. So sodium plus ionic conductivity of chloride. What if I have an electrolyte, let's suppose of the type calcium chloride? Now here what is there is you've got 2 chlorine. So that will be ionic conductance of calcium plus twice of the ionic conductance of the chloride ions, because for every 1 mole of calcium chloride we have 2 moles of chloride ions being liberated. So supposing you have to write the expression for the limiting molar conductivity of, let's say, aluminium sulfate, Al2SO4 whole thrice, how will you write it in terms of ionic conductance? Yes, it will be twice of the ionic conductance of aluminium. Don't forget the not sign on top, indicating that it's the limiting value. What do we mean by limiting? Yes, a solution having infinite dilution. That means a solution which is so dilute that further dilution does not have any effect on the molar conductivity, right? So coming back to aluminium sulfate, so twice of the ionic conductivity of aluminium plus thrice of the ionic conductivity of sulfate ions, right? Now let us go ahead with one numerical based on this. You've got a question over here. Calculate the molar and equivalent conductivity of magnesium chloride at infinite dilution if the ionic conductivity of magnesium is 106.2 Siemens centimeter square per mole and the ionic conductivity of chloride ions is 76.34 Siemens centimeter square per mole. Now in order to write, so there are 2 parts to this question. Please don't forget, we have to find out the molar conductivity as well as the equivalent conductivity. So first things first, let's start with the molar conductivity. So limiting molar conductivity of MgCl2. Just now we studied about expressing the molar conductivity of an electrolyte in terms of the ionic conductance of its, yes, the ions which are making the electrolyte. So I have written over here, so this will be magnesium plus chloride. Is this right? No? Why? What is wrong in this? Very good. Because we've got magnesium chloride MgCl2, so we will have to multiply the ionic conductance of chloride by 2. The rest is pretty simple, so you just have to put the value 106.12 plus 76.34 into 2. Please calculate, give me the value. I am waiting for an answer from you. Go ahead. Yes, I like it when you do it yourself. Very good. Yes, we've got the value of 258.80 Simon centimeter square per mole. Right? Now, coming to the second part of the question. The second part of the question is asking for equivalent conductivity. What is the relation between molar conductivity and equivalent conductivity? Simple. Equivalent conductivity at infinite dilution is the molar conductivity of the electrolyte at infinite dilution divided by Z. What is this Z? Z means the total number of positive or negative charge on the electrolyte. So, positive or negative charge which is there on the electrolyte, not and, it's or. So, when I am talking about MgCl2, what is the value of Z over here? What is the total positive charge? 2 positive. What is the total negative charge? Of course, one chloride carries one negative, but how many chloride are there in 1 mole? Yes, there are 2. So, Z is 2. So, equivalent conductivity here becomes 258.80 divided by 2. The value comes out as, please give me the answer. Very good. Yes, I am leaving it as a blank. Now a big question over here. Do I write the unit as Simon centimeter square per mole over here as well? No. It will be Simon centimeter square, but because we are talking about equivalent conductivity over here, this is gram per gram equivalent. So the value comes out as 129.44. Yes, I like the smile that comes with the correct answer when you get it right. Correct? It's a sense of achievement. Now, just now we did molar conductivity of aluminium sulfate. If I have to find out equivalent conductivity of aluminium sulfate, what will be the relation with the molar conductivity? So that will be the molar conductivity at infinite dilution divided by what will be the value of Z over here, Z or Z, whatever you may want to call it. It will be 3, it will be 2, no, neither 3 nor 2, then what will it be? Yes, it will be 3 times 2, that is 6. Or 3 times 2, that is 6. It's a neutral molecule. The total positive will be equal to the total negative in numerical value, right? So 6 here positive and 6 negative values. That is what makes it a neutral molecule. So we've got over here molar conductivity divided by 6. Okay, let me ask you one more question. If you are given the molar conductivity of magnesium sulfate, so what is the relation between the equivalent conductivity of magnesium sulfate to its molar conductivity? So molar conductivity divided by what? Very good, it will be 2 because we have 2 positive and 2 negative. So I hope this makes it clear. Are we ready to go to the next concept in Kohlrausch law? So if you notice Kohlrausch law, the first application is it helps you to determine the molar conductivity as well as the equivalent conductivity at infinite dilution for what type of electrolytes? Weak electrolytes, right? So that's the first application that you can right over here. So now since we've done the first application of Kohlrausch law, to explain the second application, I'm taking up one more numerical over here, one more question to be done. The question says you've got at 298 Kelvin, the infinite molar conductivity values are provided of HCl, it's 369.3 Siemens centimeter square per mole. Sodium chloride is 101.7 Siemens centimeter square per mole, and sodium acetate CH3COONa is 71.7. Sorry, this CH3COONa, it should be written as CH3, so 3 comes as a subscript. Now usually in your textbooks you will not find the data compiled like this. It's usually written in one line. I have compiled this data in a tabular form so that it's easier for you to understand. And the same principle you can also apply while attempting numericals based on this particular law. Believe me, it is very, very easy. Continuing with the question. The molar conductivity of a centimolar. Interesting, right? What will be centimolar? This will be m by 100. Solution of acetic acid is 14.3 Siemens centimeter square per mole. Based on this information, determine first molar conductivity of acetic acid at infinite dilution. Second, degree of dissociation of acetic acid, and third, the dissociation constant of acetic acid. Please note down the question. So when you are revising, if you browse through the questions as well at the time of your preparation, it refreshes your knowledge. So in your best interest, please note down the question, and if you want, please go ahead and give it a try. There can be nothing better than that. Go ahead, pause the video, give it a try, and then maybe you can again continue with your video to check whether you got it right or not. Okay, let's start doing it now. We've got the infinite molar conductivity provided to us. So what I'm going to do is, the data which has been given to us, I will start writing it in mathematical form. So I've got of HCl, limiting molar conductivity of HCl is conductivity of hydrogen plus the ionic conductivity of chloride, which is given to us as 369.3, gives me my first equation, right? So you can write it as the first one. Okay, go ahead. Now second one, can you split the second value as well? So you've got the molar conductivity of NaCl is provided to you. This is equals to the ionic conductivity of sodium plus the ionic conductivity of chloride. We are not going to multiply it by any coefficient because it's just 101.7 is the value. And mind you, all of these are in Siemens centimeter square per mole, but I am not writing the unit in front of it. Third, the molar conductivity of CH3COONa. This is ionic conductivity of, you want to write sodium Na positive first, you can go ahead and do that as well. Doesn't make a difference because Na positive, so because we've been writing positive and then the negative. So CH3COO negative, and the value of this is 71.7. What do we have to find out? The infinite molar conductivity of acetic acid, right? My target is to determine lambda CH3COOH. That means I need the ionic conductivity of acetate and the ionic conductivity of H positive, as simple as that. Now From which equation can I get the molar conductivities ionic conductance of acetate? Very good, from the third equation. From where can I get the ionic conductance of hydrogen? Very good, from the first equation. So I can add the first and the third equation. But what are the tag-alongs? You notice there is Na positive which is extra, there is chloride ion which is extra. So what do? Yes, I can remove the value of these two by subtracting equation number 2 from it. If you have a knowledge about Hess's law, I am sure you will be able to relate with this very easily. Otherwise, we can go step by step. So what do we have over here? Equation 1 plus equation 3 minus equation 2. You don't have to, if you want to show the minus, so this is minus, this is minus, this is cancelled out, positive and negative, this cancels out, we are left with only 2 of them. Now, the same thing you are going to do to the values which have been provided to you. So, 369.3 plus 71.7 minus 101.7. Please calculate the values and let me know the answer. Want me to leave it as a blank? We can always come back to it later. I would love for you to try it yourself. That will bring the smile. It's not just about watching the video, it's about doing the things yourself which will bring the smile. So now that we've done the first part of the question, we come to the second part. Now, first part is the same that we had done the application of Kohlrausch law, that it helps us to determine the limiting molar conductivity of a weak electrolyte. So see, we know the molar conductivity of strong electrolytes and we have been able to decipher the molar conductivity of acetic acid, which is a weak electrolyte. Oh, still looking at the blank screen, right? You want the answer? It's 339.3 Siemens centimeter square per mole. Every time, please don't forget the unit. You are now senior students. We cannot ignore the units because we've seen for ourselves how it affects the value. You got it right? Oh, very good. That's very nice. So that means you are able to understand, right? Let's go ahead with the second part, wherein we have been asked to find out, what have we been asked to find out? Yes, the degree of dissociation. Now here comes the second application of Kohlrausch law. According to this, the degree of dissociation depends upon the molar conductivity of the electrolyte at any concentration. So any concentration means concentration C divided by the molar conductivity of the same electrolyte at infinite dilution. So this will give us the degree of dissociation of the electrolyte at concentration C. Let's go back to the question and see what is provided to us. Now, the molar conductivity, it says the molar conductivity of a centimolar solution, right? This is what the question says is 14.3. That means this is the molar conductivity at concentration C divided by the molar conductivity at infinite dilution. What was the value we got? 339.3. So we input that value 339.3. What do we get over here? Yes, it's a big value. Let's round it off to the nearest 3 digits. So 0.0421, or if you multiply it by 100, we get it as 4.2%. right? It can be expressed as a fraction, or it can be expressed as a decimal, or it can be expressed as a percentage. Preferred are the decimal and the percentage value. So if you notice over here, with the help of Kohlrausch law, we can also determine the degree of dissociation or degree of ionization of weak electrolytes. So with the help of two numericals, we have done the two applications of Kohlrausch law, right? Let's go on to the third part of the question, which says that you have to determine the dissociation constant. Now, dissociation constant, you will have to go back to your knowledge about equilibrium, ionic equilibrium, and how we had modified that expression for ionic equilibrium to suit our need for weak electrolytes. So Kc, equilibrium constant, is C alpha square, where C stands for concentration, alpha for the degree of dissociation, which we've calculated just now, and don't forget we are going to put the decimal value over here. So centimolar, molarity 1 by 100, that is 0.01 molar. Alpha 0.0421 or 42 whole square divided by 1 minus 0.042. Go ahead and solve it. Now, for those students who are allowed to use the calculator, I'm sure it's a cakewalk. You would have done it very fast. But for those who are not using the calculator, it is very easy to solve questions like this using logarithms. And logarithms come in handy when you have to do physics as well. And I have shared my secret about understanding logarithms very easily on this channel as a separate playlist where I have taught logarithms. If you are facing trouble solving these type of numericals, I highly recommend that you understand logarithms through the video loaded on the channel. Now let's solve it. 1 minus 0.042, and this is the expression. Final value we get is 1.84 into 10 to the power minus 5. Now usually because it's a constant, we will not worry about the unit, although you can still give it a unit, right, based on the concentration units here. So we get the value of dissociation constant from the degree of dissociation that we have obtained from the previous part. Isn't it easy? Still a bit confused, right? So what do we do? So let's have an eagle's view of all the formulas that we have done, and we shall classify them under the applications of Kohlrausch law. So Kohlrausch law, first of all, helps us to determine the molar conductivity of weak electrolytes at infinite dilution. So if I have an electrolyte of the type AXBY, so molar conductivity is X times the ionic conductivity of the cation. So that's why I put a plus sign over here, plus Y times the ionic conductivity of the anion. Second is, it helps you to determine the degree of ionization. So alpha C is molar conductivity at a certain concentration divided by molar conductivity at infinite dilution, right? Ci, so at any concentration divided by infinite dilution. And the third formula we did was the equilibrium constant, which we have also covered under ionic equilibrium. What do you have to do in order to get a strong hold of this topic? Practice. There is no other way of understanding a topic which involves numericals other than practicing those. So please pick up any book that you have. You have your course curriculum book, you have any reference book, just at random, or even you can even pick the examples which are there in that textbook and pick up 10 questions and attempt them right now. If you don't do them right now, believe me, you'll still be hopping videos, still be trying to understand, and no purpose will be served. So please go ahead, try and make yourself happy. See you in the next video.